This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning. I just remind you that midterm will be next week, so I urge you to study. There's only 1 week left before the midterm. And yeah, just use every opportunity to talk to tutors or me before the exam test. You will get more information on LMS. All right, so I remind you that all material in the first 18 lectures will be covered by the midterm, so inclusive of lecture 18. So we will cover that lecture next week. You will have still 2 days before the midterm to cover that, but if you study everything else, one lecture shouldn't be a problem to do in a day or two. All right, so today we will concentrate on steady state errors. In particular, we will talk about tracking step inputs via so-called plant inversion and via integral control. This lecture would spend more time on investigating how we can achieve zero steady state errors when we apply step reference input or when we have a step disturbance input. So that's a very important part of design, because often zero steady state errors are requirement in design. And this is also a very nice introduction for the internal model principle, which we will cover in the next lecture, so next week. All right, so let's first just motivate this topic a bit, and then we will talk about these two methods. One is so-called plant inversion. You will see what I mean by that in a moment. And another one is using integral controllers. So integral controllers. We talked about the effects of integral control in steady state errors yesterday, but here we will just present more general statements. We will concentrate only on steady state errors. You will see that the design via plant inversion is not robust, and I will explain in which sense. And then we will see that the solution by integral control is a robust solution, and it will be preferable in most examples you consider. That's the way to go. But you know, plant inversion might still be a nice sort of addition to your toolbox, because in some cases it may be helpful. And then we will talk about that in more detail. And then we will wrap up with a summary. Actually, at the end of the lecture, I will try to connect integral control with internal model principle. So integral control that we cover in this lecture is a special case of the so-called internal model principle. And internal model principle tells you what's the structure of the controller, and what structural controller you have to use in order to achieve zero state error for inputs that are more general than step inputs. So if you have a ramp input, or if you have a sinusoidal reference, you will see that controller will have to have a very special structure if you want to achieve zero steady state error. Okay? So an integral control is just a special case of this. So in the end, I will make a connection with internal model principle as well. So why do we do this? Well, typically, one of the specifications on your design is to achieve acceptable steady state errors. It may be zero, or it may be some error smaller than a certain number. And you might be interested in particular classes of reference inputs or disturbances. Which classes of inputs you are interested in depends on the application you have. So for instance, in some applications, ramp disturbances might be common. In some applications, step disturbances may be common. So depending on the application, you would then put requirements on your closed loop performance. So often we do require zero steady state error for step inputs, either references or disturbances or both. And we will learn in today's lecture how to do that. We can do this actually in two very different ways. One is via plant inversion, and this is actually very simple, but you will see on an example, I will show you an example, that it is not robust. So you may design your system, but then if anything is different from your system, from the situation that you assume we design, then the solution will not be zero steady state error. So if you ignore disturbances, but then you end up having step disturbances, you won't have any more zero steady state error. On the other hand, integral control is a bit more involved, not much more involved, but actually the outcome is a robust design, which would mean that even if you ignore something in the design step, you will still achieve zero steady state under very general conditions. So that's a very cool thing. So this lecture is also prelude for the internal model principle, which we will talk about in the next lecture. All right, so let's talk about the first method. All right, so first thing here is, starting point is to go back to this block diagram. We considered this block diagram when we talked about sensitivity transfer functions. So in general, many control systems can be modeled in this way. So you will have some reference input, and typically R is something that you can design. You choose reference. So that's the desired value of the output usually. That's the interpretation. But then you may have all these disturbances, the input disturbance di, the output disturbance do, or the measurement disturbance, or both of them. I mean, usually they are all there, but sometimes some of them are very small and we can neglect them, we can ignore them. But typically you have all of them in any program. So for simplicity, in this lecture we consider output disturbance and measurement noise to be zero, just for simplicity, but similar arguments would apply if we consider non-zero values of these disturbances. So just to be a bit simpler, it's more manageable. So if we then set DO and DM 0, then we are left with DI disturbance and reference input. There are two inputs into our system, and if we write what the output is as a function of this reference and input disturbances, then we will have this complementary sensitivity and input sensitivity that pop up in the formula for the output. You have done the derivation of these transfer functions in one of the previous lectures, so we don't need to go through this. How do we get TO? Well, do you remember how we get complementary sensitivity? That's right. So what we do, we would, in this case, we already assume these two guys are zero. So the only possible non-zero thing is the I, right? But to calculate TO, we need to set DI equal to 0. So what we end up with is just a block diagram which is like a canonical form. It's just a unit feedback system, and the transfer function for that guy is given here. You use algebra block diagrams for the feedback correction. How do we get this SIO? We set R equal to 0, and then we repeat the same thing. So we just use the algebra block diagrams, and then you get this formula for how DI affects the output Y. So now we need to find the error. We are interested in this lecture in errors, in particular steady-state errors. So if we find what the Laplace transform of the error is, well, it's by definition. This is the definition of error. It's R minus Y. This is usually interpreted as the desired value of output, and this is the true value of the output. So if we rewrite everything, if we plug in now this Y that we obtained from the above block diagram, we get that the error now is 1 minus TO times R minus this, where this now is, if you remember, its output sensitivity transfer function. So 1 minus TO is called sensitivity or output sensitivity. Yeah? So, by the way, this sensitivity is 1 divided by 1 plus C G0. So this is something that you've seen already. all of these algebra of block diagrams is something that you should be very sort of comfortable with. So if I change this block diagram a little bit, if I, for instance, included a block in the feedback connection, you should be able to still, using the same steps, obtain different transfer functions, right, by using the same approach, right? And then the formulas may change slightly, but the underlying messages won't change, right? Okay. So this is just like an example, but it covers a very large class of systems. So what we want to do now, we want to elaborate a little bit how choices of controller, right? Well, actually, what we want to achieve is zero steady state error. Note that if we wanted to use final value theorem to find steady state error, we would need to ensure stability of the closed loop. So that's definitely one step that you need to check. So in all of this, I mean, in this feedback in general, controller might destabilize the plant. So I didn't tell you yet how to design controller, but in this lecture we assume that the system is stable. Actually, we will talk about internal stability again, but internal stability is a definition of stability that says all sensitivity transfer functions are stable. If all sensitivity transfer functions are stable, we call the system internally stable. So we will require in this lecture that all sensitivity transfer functions are stable. In other words, the system is internally stable. That's the name, internal stability. So because of the stability assumption, we can use the final value theorem via Laplace transform when we are calculating steady state errors. All right, so this is a standing assumption. By the way, if you have an example at hand, you know, it may have the same structure. If you don't check that the system is internally stable, you can't use any of these results. So sometimes students overlook this slide, they just go straight for the formulas. But you can't use formulas if you don't check that the system is stable. So please be careful about that. All right, so what we want to look at now is just sort of some examples. For instance, in root locus, we saw that proportional control, when we substituted instead of control transfer function just proportional gain, then in that case, the steady state error was basically equal to this. Again, R minus Y is E of S. This is final value theorem. I can write this because of the internal stability assumption. So I'm assuming that everything is stable. And then if we rewrite everything, we have this minus that is really 1 minus complementary sensitivity. This itself is sensitivity times Rs. So if I now assume step input, unit step input, then R of S is 1 over S. And then when I apply the formula, you know, for computing steady state error, I have to just replace S by 0. This S here, which comes from the formula, this is S times E of S. That's the formula in final value theorem. This S and this 1 over S, they cancel. And what you are left with is just what's in the brackets. So forget about R and S because they cancel. And then what you are left with is 1 minus T0. So obviously, as you let S tend to 0, what you're left with is 1 minus T0 is 0. Right. Now, T0 is 0 is what you just substitute instead of S, 0 everywhere. So if your transfer function is 1 over S plus 1, you just substitute S 0, you just get 1 over 1. And that's your T0, right? So T0 is given here, and depending on the G of S, T0 can take different values. So in general, note, if I pick the plant as, you know, generally and controller in general, note that when I substitute here instead of S0, puts S0 here and 0 here, I get KG0 over 1 plus KG0. Well, this in general would not be equal to 1. K can be anything, G at 0 can be anything. It's an arbitrary plant. So in general, you cannot expect that this T0 at 0 would be exactly equal to 1. If it happens to be exactly 1, you will have zero steady state error. But, you know, often it's not. Right? So suppose that, you know, we have that this thing here holds, so the steady state error is not zero. We want to now see how can we address this issue? How can I make steady state error zero? So there are two different ways. Here we will pursue one way which basically says, you know, what is y? Well, y is something that generates this term t0. By the way, this 1 comes from r because I took r outside. So r times 1 is exactly this r. And then this y, it can be related to r through this formula. So it's t0 times r, right? So that's my y. So note that if I scaled, you know, this part, so this input here with a constant, you might end up with a different value for y. So you may, suppose I just pre-multiply everything with a constant, you can actually find that constant times t0 gives you 1, and you can choose constant so that you make it 1. So that's exactly what this Planck inversion is. So what you can do is, you can pre-multiply everything by 1 over t0 at 0, assuming that t0 at 0 is not 0, right? So you can't divide by 0. But if you do that and you repeat everything, what you get is that this t0 would now appear in the denominator here. You still have t0 of s, but then since you're applying final value theorem, when you let s tend to 0, this will evaluate to t0 at 0. So you get exactly that steady state error is 0. So this is basically a trick, a hack, that, you know, gives you zero steady state error. And what you did, you just pre-multiplied with a constant. This is just a number. This is just a number, right? Constant gain, right? Now, what are the issues with this scheme? I will now present sort of some extra analysis on what happens when, so we ignore the disturbance. So the question is, well, if we have disturbance, would I still get zero steady state error? Well, you won't. So if I now have this hack, you know, pre-multiplication, this was there because I wanted to kill the effect of the reference, right? Reference was not giving me steady state error 0. But if I now have disturbance, I repeat all the calculations. If you do all the steps carefully and apply step disturbance and step reference, you would find that steady state error now is equal to this, which is now not 0. So what does this tell you? Well, the hack or this design is not robust. So we ignore disturbance in the design, right? But when we have a disturbance, we don't know whether we will have disturbance or not. But if there is some disturbance which we didn't consider in the design, we get non-zero steady state error, right? So it's not robust. That's one issue, and I will go through this issue again in another more specific example. But what is another issue? Well, what is this T0? Where does this T0 come from? Well, if you go back, T0 depends on the controller gain. You can pick the controller gain and you can be quite certain what you picked and implemented. Right? So K, you can choose yourself and you can be certain that the value you are using in the analysis is close to the true value of K. But G of S is your Planck model. Now, the problem with the Planck model is we never, ever know exact model for the Planck. We are always using something that's close to the model, but it's not really exactly the same as the system. So note, if you have that you are using in your design some model for G, but then your true system has a different G, right, different model, then the T0 that you calculate using the model would be different from the T0 that you need to make everything, all the steady state error 0. So note that this design is also not robust to Planck uncertainty. If there are some errors in the model, that would again give you non-zero steady state error. So, but I'll concentrate a bit on disturbances in the examples. So let's look at the this example, by the way, this example is exactly the example we used in PID control. It has 3 poles at -1 and no zeros. So we now are going back to that example to analyze how this plant inversion affects zero steady state, or steady state error. If we now apply this method to this example, I apply step input, so R of S is 1 over S. I apply my final value theorem, and I get this. So in this case, steady state error is 1/2. But if I calculate what T0 at 0 is, it's 1/2. How do I see this? Well, T0, if I sort of expand this, polynomial, and I apply formula for T0, right? Then, I would get this. Here I'm using k equal to 1. So substitute that G of S and that k into this formula, and in the denominator what you get is what, that polynomial I gave you, right? So you can calculate T0 of S from that, G0 and k, which is equal to 1. So now, what does this mean? Well, we need to pre-multiply everything by 2, which is 1 divided by 1/2. That's 2, right? So if you repeat all the calculations, indeed, we pre-multiplied everything with the right number, so we get steady state error 0 when we pre-multiply by 2, right? For unit step references. But if we now consider a disturbance and I complete all the calculations, you see that the steady state error is -1/2 when we have both step disturbance and reference step inputs. So reference is a step input, disturbance is a step input, steady state error then becomes non-zero. So how does this look in simulations? Well, if I consider step response without feed forward and without disturbance, so this is basically, this blue line is the step response for the original setup. So there is no feed forward and there is no disturbance. That's the blue curve. Let's look at the steady state error from simulations. So where do we want to converge? Well, we want to converge to 1, but where do we converge to 1/2? So the steady state error is the difference between 1 and 1/2, right? So that's 1/2. That's how we can see directly from the step response when we plot it what the steady state error is. When we scale everything with the feed forward, but we don't have disturbance, we get the red response. This response corresponds to this situation. So we scaled the reference, but we didn't have disturbance. And what we see in the step response is indeed this red curve, and know that it does converge to 1. That's where we want to converge, so 0 steady state error. Right? And then when we have the feed forward and disturbance, that's the last picture, the step response is given by the green curve. So now we converge again somewhere else, right? We sort of accounted for the references to feed forward, but now disturbance hits us, and then again everything breaks down. When I say that this approach is not robust, I think about disturbances or I think about plant uncertainty, but I concentrated more on disturbances. So this is all good. By the way, reference input is a unit step in all cases. In this case, and I also used, in the green case, I also used step disturbance. So in the green case, I had 2 step inputs into the system. And I just simulated the outcome. All right. So what we can conclude from all this analysis? Well, several things. Feed forward scaling, like this plant inversion, can yield 0 steady state error, but the solution is not robust. If there are any input or output step disturbances, or any other non-step disturbances, the steady state error would in general be non-zero. And also, if we have plant uncertainty, if the model that we are using for design is different from a true plant, right, you will again not achieve zero steady state error with this approach. So what we want to do is we want to present a better solution which is robust to both step disturbances as well as plant uncertainty. So if the model of the plant is slightly different from the true system, then we want to have a controller that still gives you zero steady state error, even if you don't know what the exact plant model is. Okay? So that would be a very useful result, and that result indeed exists. That's the second method. So we will talk now about achieving zero steady state error by integral control. Are there any questions on the first method? Yep.
When you 1 minus t naught is equal to t naught 0, we multiply t forward by 1 with t naught. Why is the 1 naught? So it's odd. So go back to the t forward sequence. So yeah, this one. Why is the 1 naught multiplied by t naught as well? Is the r change by 2 times it by 2?
Yep.
Then it should be 2 over s times it by the 1 minus t naught.
Well, just think about it. What is the definition of the error? The definition of the error is r, the original r, the one in the beginning, minus y. That's the definition. And the only effect that this block, extra block has is on y. The definition is r minus y. That's why. I like you asking questions. Thank you. Any other questions? All right, so let's learn a more powerful, more useful method for achieving zero steady state errors. So we will talk about integral control. We've already announced in previous lectures and saw some examples where integral control was shown to give us zero steady state error. Now we want to analyze it just in a more general context. So you will see that integral control yields zero steady state error to unit reference signals. Now, as I remind you that stability is an underlying assumption for the whole lecture. So the controller was chosen so that all sensitivity functions are stable. That's the assumption, right? So now this solution is robust in the sense that if there are any input and output step disturbances, steady state error to unit reference will still be 0. And this is not the case in the previous design approach, right? And this is also a special case of interval principle. Now, what I didn't show here, but we will discuss it as we go, this solution here is also robust when we use an incorrect model. So suppose you use an incorrect model for the plant, like it's slightly off. You design controller for the model, and you do simulation, everything works, right? When you use controller on the model. Then you need to go and use the same controller on the true robot or airplane or a car. Now, the true system is different from the model you used. But if the controller stabilizes still the true system, right, then you will see that existence of integral control will still give you zero steady state error. So this solution is also robust to plant uncertainty. As long as the controller stabilizes the true system, you'll be good. Right? So that's a very, very good news. And you will see that this is very, very sort of special case of a much more general principle, which says, you know, if you, so I'm telling you, if you want to track step references using integral control, but I can also tell you, if you want to track sinusoidal inputs at a certain frequency, then the controller should contain certain poles that would generate that sinusoidal reference, right, in a particular way. I will explain. So the controller needs to contain internal model of the disturbance. And that's how you know that integral control and step disturbance have the same Laplace transform, 1 over s. So integral control is 1 over s, and reference input is 1 over s. So, and then controller needs to contain the model of the disturbance. So we will talk about that in the next lecture as well. All right. So let's talk about integral control. So now I'm just using for simplicity integral action in the controller. I have the Planck transfer function. I apply step reference, so R of S is 1 over S. Steady state error is 1 minus T0 at 0. So when G0 is not 0, you will find that T0 at 0 is 1 for any values of the gain. How do we see that? Well, T0 at S is really Ki G of S, and then S plus Ki G of S. How do I get this S? Well, the open loop transfer function is Ki over S times G of S. So I have here Ki over S times G of S, 1 plus Ki over S G of S. That's the algebra block of diagrams. I just cancel S's, so S pops up here, but I cancel the two. It's like a double rational function. I cancel S, and then I get this. So if G at 0 is not 0, then no matter what Ki I use, as long as it's stable, I get that T0 at 0 is 1. This is a very cool observation, It's like a magic that comes out of maths, right? So just because I use integral control, my complementary sensitivity function looks like this. So when I evaluate it at 0, for very large class of plants, I just require that G at 0 is not 0, right? I get that T0 at 0 is 1. Obviously, I'm also using here, not just G0 is not 0, Ki times G0 is not 0, right? So Ki should also not be 0. But that's, obviously, if I put Ki equal to 0, I basically cut out the loop. I mean, now it's an open loop system. It doesn't make sense. I want to control the system with some non-zero Ki, right? So that's a very, very cool observation. But note here, I did not use any disturbance. Now, the million-dollar question is, well, what happens when we have disturbances now? Let's repeat the same calculation. So if we have now disturbances, so both references and disturbances are unit steps. So I use 1 over S for both of them. I plug in, all these into the formula for error. So in that case, I get that the error is this bracket times 1 over S. What's inside the bracket? It's 1 that corresponds to R, right? And then we have minus T0 that corresponds to Y, right? And then this term here corresponds to DI, right? Now note what we have here is this S and that S would cancel, right? And now I'm saying, well, what happens to the bracketed term when I let S tend to 0? Well, T0 at 0 would be 1 under general assumptions that Ki is not 0 and G0 is not 0. Right? But this guy has S in front of it. So when I set S equal to 0, that would be 0. So I still have 1 minus 1, right? Minus 0. I get 0 steady state error even when there are some step disturbances. So in other words, I didn't take disturbance into account when I was done in the controller, but even if there is disturbance, I'm good. That's a very cool outcome of the design. Now let's consider another interesting sort of thought example. Suppose that I use G0, which is my model, right? And I design controller Ki over S so that G0 is stabilized, my model is stabilized. Then this analysis shows that, yes, indeed, I would have 0 steady state error. Because I didn't place any condition on G0, right? So this can be very general, right? Now suppose you apply this control that you designed on G0, on the model, you apply to the true system, and I call the true system G. So G is different from G0. But suppose that these two guys are close enough so that the same controller stabilizes both. Well, since the same controller now stabilizes both, then although I don't know what the true Planck system is, right? I stabilize it, and I can conclude 0 steady state error. So in other words, this integral control would be robust to plant uncertainty as well. That's a very, very powerful design. It ticks off so many boxes. Yeah? So by the way, in this lecture we are concentrating on steady-state errors. So if in an example, in the exam, you are asked, achieve these specifications, and then say, what specifications say, 0 steady-state errors to step inputs, you would know immediately that you would need to play with integral control. Right? Or you need to check whether the plant has an integrator. If the plant has an integrator, you may be fine. We will learn about that in the next lecture. But you will have to somehow either impose integral control, or you need to check if the plant indeed has integral action. But then it just tells you that your controller will have to have integral action in it. And then you will still be, so you impose that integral action, and then your specifications say, but you also need to achieve settling time of 2 seconds, overshoot of less than 10%. Now, with this structure of the controller, you need to achieve all these other things. Right? So this sort of decouples the design. You can address steady-state errors just by imposing certain controller structure, and then you can address all the overshoot, rise time, settling time by tweaking the parameters in the controller using root locus, for instance. Right? So this definitely is, important in a range of problems, and you'll probably get it in the exam. All right, so here is an example. So what I'm doing now, I want to show, I'm revisiting the example which we considered in PID control. This is the same plan, but now I use PI control. So this is a PI controller. This control is a PI controller. If you do all the analysis, you can first show that this controller stabilizes this plant, right? That's the first thing. And then, you can, using those results we already presented, you know that the steady state error will be 0, but when you calculate everything in this example, yes, indeed, you get 0. If you now do the same controller, we test it with disturbance and reference, you again do the calculation for the example, when both of these guys are step signals, this is a step, that is a step, you still get to 0 steady state error. So on this example, we basically check that what we stated is correct. Cool thing is, well, you simulate things. So the PI controller with 0 disturbance and unit step reference is given by the blue curve. The PI controller with unit step disturbance and unit step reference is given by the red curve. So what we can see from this is that when we have disturbance, it indeed disturbs us. The overshoot is larger. Right? So the transients are not identical in the two cases. But both of these achieve 0 steady state error. Right? And that's a very, very good message for us. So if you want to design robust controller that achieves 0 steady state error, integral action is the right way to go for step references. Now, if I note that all of this discussion was tied to step references, integral control. If I decided to change reference inputs like ramp references, then integral control will not give you steady state error 0 in general. You will need to maybe use double integrator. Why is that? Well, how do we model a ramp signal using Laplace domain, right? It's 1 over s squared, right? So you need to then have a model of 1 over s squared, which is like a double integrator, in the controller. We will present a general sort of statements in the next lecture where we look at internal model principle. Now look, it's very useful to summarize now all of these things. So integral control, so I shouldn't say here open loop. So integral control, so what I mean by open loop, if either a plant or controller contain integrator, then you will have 0 steady state error for reference inputs. So, for instance, if the plant was just a single integrator, you can show that a proportional controller yields zero steady state error. But the plant already has an integrator in it, so controller didn't need one. We will present a more general set of rules on how to approach this, how to do it in general in the next lecture. So note that we get zero steady state error even when we have step disturbances. And by the way, everything I did here, all the calculations, were only for step input disturbances. I could have had both step input and step output disturbances, and the outcome would be the same. As long as I have internal stability. What is internal stability? All sensitivity transfer functions are stable. As long as I can apply finally the theorem and everything is stable, this rule holds. So integral control would give you zero steady state error. So what I presented in the lecture is a special case, so this more general case, right? When I have that I apply reference input step, input disturbance step, output disturbance step, I will still have zero steady state error, as long as I have internal stability. Very, very useful result. And now, I want to use just a few last minutes of the lecture to link this result to the internal model principle. So this is a special case of internal model principle. So I want you to think about integral control in the following way. Note, what I'm doing now is something which we never did before. I'm using my notation. Usually R would be given, like arrow would be named R. So a certain arrow represents a signal, and then R, which is a reference, which is a signal. But in this case, I'm saying, let's think about R as an output of an integrator with zero input. If I have an integrator, what is the integrator sort of model? Well, Y dot is equal to U. U is the input, Y is the output. That's the integrator equation. Yep, so let's see whether I can find. So if I consider an integrator, 1 over S, I have Y, I have U, right? So I can say here, this is U of S, this is, let's say, capital Y of S. What is, from here, I have that Y of S times S is equal to U of S. Can everyone follow that? That's just from the transfer function. So the output here is U times the transfer function. I just take S on the other side. So I get, from this model, I get that S times Y of S is equal to U of S. If I take inverse Laplace transform of this, I get, so take inverse Laplace transform of that, I get Y dot is equal to U. This is in time domain. Right? What this equation in Laplace domain means for zero initial conditions is exactly this. Y dot equal U. What is the solution of this equation if I set U equals 0? So now I let this to be 0. What is the solution of this equation? Constant. The constant will be equal to the initial condition. Right? If I integrate this equation here, y of t is equal to y at 0. It's the initial condition. I can pick initial condition myself. So how I can think of step reference is like the output of a block to which I apply input 0. Yeah? So that's why I sort of put input 0 here, and I'm saying the output here, well, or I'm saying, and I'm using notation, I'm saying R of S is 1 over S. So I can model R of S as the output of an integrator with 0 input. Similarly, for this disturbance here, we are talking about step disturbances. Again, I can model it as the output of a block integrator with 0 input. Now, where I want you to pay attention, what is the transfer function of this sort of generating a block? So block that generates reference. It's 1 over S. If we think about this as a transfer function of this generating block. But note now what we observed in the integral control case is that in order to have zero state error in a robust sense, we have to have internal stability, and controller has to have a certain structure, which is VS over ALS. There are some polynomials, right? But I have to have 1 over S. Integral control means I have to have 1 over S inside the model of my controller. And that's the same 1 over S which generates these inputs with respect to which we want to have zero steady state error. This is a special example, special case of internal model principle. Why do we call it internal model? Because the model of disturbance and reference are internal to the control model. Yeah? We will see later on that, for instance, a sinusoid can be generated by 1 over S squared plus omega squared from Laplace transforms, right? The cosine, sine, cosine can be generated this way. So if you want to then track reference signals that are sinusoidal of a certain frequency, then you have to include inside your controller the model of that disturbance or reference that you want to track. And you will see that that is a necessary and sufficient condition if you achieve stability. Internal stability, this will be also then sufficient condition for achieving zero steady state error for that class of references and inputs. We will present this in a much more general case in the next lecture. All right, so just a quick summary. What we saw is that tracking step references can be achieved either by Planck inversion, so just multiplying with a constant, or through integral control. I'm talking about step references and disturbances. And this is actually just a prelude to a much more general approach for robust tracking of much more general classes of references and disturbances, which is called internal model principle. Right? All right. Any questions? Yep.
So, can you please repeat how integral control eliminates uncertainty in the model?
So the question is how integral control copes with uncertainty in the model.
Yeah.
So let's go back to this example. So suppose that I'm using, let's say, this example. It's a, well, maybe even, this example. So suppose that the model was S plus 1 to power 3 in the denominator. That's the model of the clock. I designed this controller so that this model is stabilized. Now, if the Planck model is slightly different, so I don't have 3 poles at -1, but I have 1 pole at -0.99, 1 at 0.95, 1 at -105. We can check whether the same controller stabilizes the true model, which you don't know, right? You don't know what the poles of the true Planck are. Maybe there are also zeros. As long as the controller stabilizes the true Planck, you will still achieve that zero steady state error, right? So, and by the way, I mean, we didn't talk about robustness and things like that in terms of polynomial solutions. If you think about how you calculate poles of a transfer function, you have to solve, some polynomial equation. Now, if your model has certain coefficients, but your true system has slightly different coefficients, well, small perturbations in the coefficients of the polynomial would result in small perturbations on the solution of the polynomial. And hence, you can see that, if your Planck model is close to the true system, you will still stabilize, right, using the same controller, right? So, and then the analysis is the same. So we can, what this says is we can cope with small Planck uncertainty and still achieve the same result. Any other questions? All right, thank you very much. I'll see you this afternoon. Or not. Let's just go outside.
And you like put some time to it. I mean, we just saw it time down. Did you come back up?
Yeah.